Thanks everyone for joining. Today we're going to be looking at one of the modules within Inventor Nastran called Nonlinear Static. This is one of the greatest benefits really of going up to Inventor Nastran from a standard FEA platform is that you get the ability to really do these more advanced analysis types. We'll be focusing on a couple different scenarios that would classify your analysis as being nonlinear and sort of how you can approach that. And then I'll also give you guys a couple of pointers as far as when you start running a nonlinear static analysis, some things to look out for and some things that will make things run smoothly for you when you first start dipping your toes into this. So first couple slides here, I like to show these with all the webinars that I give, just so you guys kind of have a background of what Inventor Nastran is if you're not familiar already or already using it. So you have some background on where it came from. Really, it was originally created for NASA in the 60s. MSC was the original developer, and then it sort of was acquired by Autodesk and then embedded into Inventor. So it was originally sort of a standalone software, and you can still buy it as a standalone software. This version of Nastran that Autodesk acquired, they built into Inventor. So the nice thing with that is even if you're not doing your design work in Inventor already, it's really easy to bring in part files from other softwares as well. You can do all of your 3D modeling and your assembly and your measurements with Inventor as you normally would, and then you can just immediately jump over into the Nastran stress analysis environment without having to export out your parts and have several different working versions going. So it helps you keep your files organized, and it just is a really nice, smooth workflow. Looking at some of the things we can do, obviously you've got the basics, right? So you've got your linear statics, you've got your modal analysis, and these are two things that you can do with your standard Inventor FEA. So if you go to stress analysis within Inventor, you will see the ability to do linear static and modal. So those are pretty common, when you're just looking at simple stresses, simple load cases, and modal analysis where you want to get some natural frequencies. You'll also notice then with Nastran you get the ability to do nonlinearity, so we're going to be focusing on that today. A couple different things you can do there. One is impact and drop test. We're not going to be focusing on that today, but we may do that in a future webinar. And then also permanent deformation, plasticity, large displacements. That's what we will be talking about today. And that is a really awesome module that they've added in. You can also do some more advanced things. Maybe you need to look at some buckling. You want to look at some geometric instability. You can run buckling analysis. Fatigue. So maybe after 100 cycles, your design is functioning as you'd expect. But maybe in the field, you've seen some failures after you hit that 400, 500,000 cycle range. Maybe you want to run some fatigue analysis to see how you can improve your design so that when it does get used and abused out in the real world, you can at least have a better gauge for how long you can expect your parts to last. And then you really get some cool stuff with thermal as well. We're not going to focus on that today either, but you can do some basic thermal analysis. If you do need to kind of combine stress and thermal, you can do that as well. So moving right along, some things when you're comparing directly Inventor FEA and Inventor Nastran. So maybe you're already using Inventor FEA regularly and you purchased the product design and manufacturing collection, so now you have Inventor Nastran as well. What do you really get? Is it worth jumping up and using Inventor Nastran and learning the new software? In a lot of cases it is, because you get a lot more. You get things like mesh quality checks. You can make sure that you have a really high quality mesh. There's a lot more mesh features and mesh controls that you can apply. Part-based mesh, which is great when you have an assembly. Let's say you have an assembly of 50 or 60 components. Great to be able to apply mesh controls based off of part rather than having to select surfaces. This is great because you can apply a specific sized mesh to each part rather than having to do a global mesh and then change faces. You also get a lot more ways to connect things. Rigid connectors are a great way to simplify connections and avoid having to use as many parts in your assembly analysis. And you get a lot more analysis types as well. everything from vibration, shock, fatigue, as well as our nonlinear analysis, which we'll look at today. So please, feel free to reach out after the webinar if you have any questions about, getting set up with any of these other analysis types, or if you're looking for more information on Inventor Nastran and sort of what it includes, feel free to reach out if you haven't already. All right, so let's jump into our nonlinear statics. So a lot of times when people think nonlinear statics, the first thing they think about is nonlinear materials. So when you push your analysis to the point where you're loading your part and it's seeing a stress that goes beyond the yield strength of the material, you're going to be working in the nonlinear working range of the material at that point. And that's where linear static analysis starts to break down. So that's one of the conditions, but there are actually 3 conditions that can reclassify your analysis as being nonlinear. So this is any of these. If any of these are satisfied or you think they might be satisfied, it's likely that your linear static analysis is no longer providing accurate results. So the first one is going to be our geometric nonlinearity. So that's when we have large displacements, we have large deformations, and that's not something I can put a number on. I can't say, when you see 2 inches of displacement, you should switch to nonlinear. That's not the case. Really what it comes down to is, in reference to your overall size of your model, how much deflection is happening. Typically, once you start seeing deflections more than 10, 15 degrees or so in components, that's where you'd want to consider nonlinearity. And anytime you have a larger amount of deformation that occurs, it's worth running a nonlinear static analysis to see how it compares with your linear static results. It's also going to break the load up, so it'll actually capture that displacement value with more accuracy, and you'll see more accuracy in the stresses as well. Material nonlinearity, like I mentioned, is a key factor with nonlinear static analysis. This is things like plasticity, nonlinear stress strain curves. Anytime you push your stress beyond the yield strength of the material on any of your components, you might want to consider using material nonlinearity. So to do that, you'll have to take your materials and apply some data points for your stress strain data. So you need to give the solver some data points to reference so that it knows how to interpret the stress strain curve once you get beyond the linear working range of the material. I'll talk about that more in a second. And the last thing is boundary condition nonlinearity. This is another nonlinear condition where you have loads or constraints that are moving around. So you have things shifting around and unstable. You also might have contact interaction. So what happens is sometimes you have parts that are sliding or rotating because they're not fully constrained. That's okay, but in order to capture that sliding, maybe you have a part that rotates around and it's bouncing, or it's connecting with another component and creating new contact. That is something that is considered nonlinear. With a linear static analysis, everything that's in contact at the beginning of your study is assumed to remain in contact and not change. It's not going to be using the solver to search for new contact areas, whereas a nonlinear static solver, at every single iteration, it checks for new contacts. So this allows us to look at things like snap fit. We can look at hinged components that are rotating or swiveling or pivoting around. We can look at parts doing impact analysis. Anytime we have large displacements and sliding, usually there's going to be some new contact that's being created. So geometric nonlinearity, this is the first one. Again, what the solver is going to be looking for are these 2 things, stress stiffening and large deflections. So it's going to capture the displacement accurately. It's also going to capture the effects of stress stiffening, and this is a really important measurement that it'll be taking. So looking at this part right here, this is a simple surface, just representing like a drum membrane. If you were to run this simple surface with a point load in the middle in linear statics, you'd likely get a result that looks like this, where you have a really exaggerated amount of displacement. And I think in this case, it was something like 1,000 inches. So it starts to displace, and the element stiffness never changes. So the load path continues along the same vector. The elements displace evenly. using just the linear relationship in the material. But with nonlinear statics, what happens is you get a result that looks more like this, because what happens is the elements around the edge of this membrane, at the very beginning of the analysis, if you were to look at one of those elements, let's say this is the edge of the membrane and you're loading it at the beginning of the analysis sort of in the vertical direction. So you're loading it such that you're sort of bending those elements. But as the analysis continues, what happens is that element starts to deflect downwards so that the load path is no longer just in bending, it's almost pulling on that element in tension. So as the orientation of those elements changes, with nonlinear static analysis, it recalculates the orientation of that load and how it's pulling on that element. And so that element may show signs of stiffening as the load being applied changes orientation. So that's sort of what stress stiffening is, and that's what will be taken into account with nonlinear static analysis, and that's something you wouldn't get with linear. The second nonlinear condition is our material nonlinearity. With a nonlinear static analysis, typically what you're going to want to do is if you're seeing stresses beyond the yield strength of the material, you'll need to reclassify your material as one of these three options here. So if you're working with like an elastomer material or a rubber, it's likely you'll be using a nonlinear elastic. If you're doing a metal, so maybe like aluminum or steel, you're likely going to be using one of these two plastic curves, either bilinear elastoplastic or multilinear plastic. With bilinear elastoplastic, you're taking your true stress strain curve and you're approximating that nonlinear working range. So rather than entering in all the data points, you're basically just estimating where the fracture point is going to be, where the yield point is, and then you're going to be calculating a tangent modulus that's typically somewhere between 7 to 10% of your true Young's modulus. So it's going to flatten the curve back out, and you're basically just estimating that nonlinear working range. This is really a pretty good way to look at materials when you're first getting into nonlinear static analysis. It is an approximation, so it's not going to be perfect, but it does give you a good representation of which elements go plastic, and it'll give you an approximation of the amount of displacement that occurs due to that deformation. This is also a great way to look at aluminum materials, because typically aluminum materials will have a nonlinear working range that's fairly flat. So its nonlinear static curve will be close to your tangent modulus approximation. Now, when you start getting into materials like steel, where you have a significant nonlinear working range, and you might see what's called necking. So with a steel material, what you might get is a curve that starts to work harden. You may see what's called a necking region, where it flattens out and then continues to work harden until it fractures. So for steel materials and more complex nonlinear static curves, you're going to want to use a full multilinear plastic model. And for this, you need to go in and actually input in your stress and strain data points after you hit yield. So it'll give you the first data point in the table, which is essentially this point in the curve on your linear static curve, right where it hits yield. And then you have to input in data points beyond that for the software to follow. So anytime you're looking at nonlinear plasticity, so you're looking at permanent deformation in your models, you'll need to reclassify your material and add in some additional information for the solver to use. And the last type of nonlinear conditions is going to be your boundary condition nonlinearity. This is where your loads constraints or the orientation of your loads change during your solution. So you're going to be having enough sliding or rotation that the load path changes. You also might be getting nonlinear contact, which means new contacts are being created. So you're getting parts that are pivoting and sliding and bumping into one another throughout the analysis. And that changes at every single increment. So it's not a constant interaction, which means new contacts will be created, and some contacts that started at the beginning will then start to not be used anymore. So it's going to be constantly reevaluating all of your contact surfaces and looking for new ones. This is great for snap fit, So I'm showing this example down here, which we're going to look at closer in a second, of a buckle, just a snap fit buckle representation. And you can see at the beginning of the analysis, it starts to slide into the buckle and you get contact where the snap is being pushed back. And then at the end of the analysis, it starts to push through the buckle and the load path and the stress change to be more along the middle of the buckle as it starts to snap through that fitting. This is something you can't do with linear static analysis because the solver wouldn't be able to solve, that half-inch displacement all at once. You need to run it through nonlinear static so that it can calculate all this new contact that's occurring at every single increment as this buckle snaps through the fitting there. Before we get into our demo here, I wanted to give you guys some pointers, some helpful tips that are really important when you start running a nonlinear static analysis, and some things you might run into when you do start doing that. The most important thing, and the reason I put this in bold, is because it is a really helpful tool that a lot of people don't think about when they start running nonlinear static analysis, and that's using your constraints to limit unnecessary translation and rotation. So when we get into Nastran, I'll show you guys what this means. But essentially what I'm saying here is if you have a part that you are looking at, maybe it's bending along the x-axis, you might want to limit some of the translation and rotation about other axes in your model so that the solver doesn't have to calculate all of those displacements and rotations. It limits the motion so that you're only bending in the direction that you like to see or that you're most concerned about, and it saves the solver time. So instead of taking an hour or two to run your analysis, it may reduce that down to a matter of 10 or 20 minutes. So try to use your constraints to limit unnecessary rotation and translation. Load increments are also very important. When you run a nonlinear static analysis, you have to specify a number of load increments. These are just sort of guidelines. I wouldn't, take this as being, the holy grail of load increments for Nastran, but I have found in the past that anytime you're looking at large displacements, let's say that's your only nonlinear condition. So you don't have new contacts being created, you don't have any material nonlinearity, the only thing you're observing is a large deflection in a part, you're probably only going to need 10 to 15 load increments. It's fairly easy for the solver to calculate that. Now, if you start using a analysis where you have some material nonlinearity, maybe you have some permanent deformation in your model, usually you're going to have to jump your load increments up to somewhere between 20 and 30 in order for the solution to converge. So it basically has to converge every single load increment. The more increments you use, the easier it is for the solver to converge those results. And I found with material nonlinearity, usually 20 to 30 is going to be a good place to start. You may have to go higher. I'm just saying that you should at least start with 20 to 30 before you go any further. And then lastly, when you have new contacts being created, maybe the combination of all three of these, but especially when you have a snap through, a buckling, a sliding hinge, anything like that you're looking at where a lot of new contacts are being created constantly throughout the analysis, you're going to be needing probably 50 to 75, maybe even more than that. But usually 50 to 75 increments will help to get you a nice converged solution for that type of study. So just some pointers there with load increments. Nonlinear materials, if you are doing a nonlinear material analysis, I recommend starting with elastoplastic. So this is your curve where you estimate that tangent modulus. I recommend using either the default tangent modulus, which is going to be 10% of your Young's modulus, or if you have test data, you can calculate what that tangent modulus is by looking at your ultimate tensile strength and your yield strength and calculating that curve. And that's a good place to start because it's going to give you a really nice representation of which elements will be going plastic and generally what displacement you'll be seeing. If you need the accuracy to be much higher, that's where you'll jump into full plastic. But before you do that, start with bilinear and just make sure your analysis is running properly and you're seeing deformation where you would expect before you go and you define a full plastic curve. And then lastly, I had a question come up about this a couple weeks ago from a customer that was running nonlinear static and having trouble getting a result. If you have a large displacement that happens rapidly, so let's say you're applying a force to a component that's pretty unstable, so it's going to be twisting or bending or rotating really quickly. So as soon as you apply that load, it really starts to bend. Maybe a thin sheet metal part or a plastic component that bends really quickly under load. When that rapid displacement occurs, sometimes the nonlinear static solver has trouble. So first thing you should try is to bump up your increments. But if that doesn't work, I recommend jumping to a nonlinear transient analysis, which is going to be time-based instead of using load increments. So you'll be applying a time step, so it's time-dependent, and it's going to be a much more accurate solution. It may take a little bit longer to solve, but it will help to capture that rapid displacement with more accuracy than a nonlinear static solver will. So just keep in mind when you have those large, quick displacements, consider jumping over to nonlinear transient and looking at it in a time domain. All right, so let's look at a couple scenarios here. So I'm going to go ahead and open up the software here so we can get out of the PowerPoint. And the first one I want to look at is this flex test. This is actually from an example we use in the Nastran Essentials course that I imagine it provides. And this is a really good example of where you might see nonlinear materials being used. So what this is actually half of the overall model. So the full model has the other half of this pin here, and then the bar, and then another support on this end. So this is really just half the model. So it's a symmetry model. But essentially what we're doing here is taking this pin component right here, displacing it downwards 35 millimeters. And this bar here is ABS plastic. So when this pin, this steel pin, is pushed down into the middle of this plastic bar, the bar is going to deflect. So if you had it pinned on two ends, the bar is going to deflect down in the middle to a certain amount, so all the way down to 35 millimeters. And it's going to show permanent deformation. Displacing the middle of the bar that much is going to cause elements in the middle of this bar to go beyond their yield point and go plastic. And so when they go plastic, that means they're just going to permanently deform. And that shape that it takes will then be permanent. So what we can do with nonlinear static analysis is, number one, we can look at this large displacement. So 35 millimeters is quite a bit for this model. And if there's going to be a significant amount of bending occurring. So we'll be getting large displacements. We'll also be seeing, to some extent, stress stiffening on the elements out here at the edge of the bar, where at the beginning they're being loaded and bending, and then at the end of the analysis they're transitioning into being loaded in tension. And the third thing we'll be observing here is nonlinear material. So this bar here, if you look at this material, this is just a simple ABS material, so it's ABS plastic. When you're defining your material for nonlinear static, you have this analysis-specific data section. If you go into the nonlinear range, you can specify either an elastoplastic curve or a plastic curve for this material. In this case, a plastic curve is defined with really just one additional data point. So when you're defining your curve, if you click Show XY Plot, it'll show you what that is. And for this material, basically what we're saying is as soon as we hit the yield point, it's going to go flat, which means it's going to become a perfectly plastic deformation, which means as soon as an element hits the yield strength, it's going to then basically no longer have any additional strength. It's just going to deform permanently at that point. So it transitions immediately into a permanent plastic deformation. So looking at your curve to make sure that it matches your material data is always a good choice. And what that means is in the middle of this bar, some of these elements will show permanent deformation. Now, the cool thing with the nonlinear static solver is subcases are treated a little bit differently. So when you have two subcases, so in this analysis, we have subcase 1, which is called flex. Subcase 2 is called release. The subcases pick up where the last one left off. So it's going to deform the bar 35 millimeters, and when it gets to subcase 2, it starts with the bar deformed 35 millimeters, and then begins the next subcase. So it starts at where the previous subcase left off. That's different from the linear static solver. The linear static solver treats each subcase entirely independently, so you have a result set for each subcase. But with nonlinear statics, they compile upon one another. So the advantage of this is in subcase 1, we're going to be displacing this pin here 35 millimeters. In subcase 2, we're going to change that displacement to 0 millimeters. So what it's going to do is it's going to displace at 35 millimeters. In the second subcase, it's going to bring it back to a 0 millimeter displacement. So it starts at negative 35, and by specifying 0 for our second load, it's going to move the pin from 35 millimeters back to 0 throughout the second subcase. So the neat thing about this is we'll get the result set for the first subcase, deflecting the bracket, or sorry, deflecting the beam. The second subcase will show the pin moving back to 0. This is 0 right here. And then what we'll see is if this beam doesn't go back to its original position, we will see that permanent deformation in the result set. So if we look at the results, you'll see increment 1 through 20. So we did 20 increments for the load, and then 20 increments for the release. So looking at load case 1, increment 20, so this is at max deflection. So this should be 35 millimeters of deflection. Look at this from the side. This is the actual deformation. So you can see the pin displaces 35 millimeters. It bends the beam, and we can see we've hit our yield strength in all these areas that are red, which means we're going to be seeing some plastic deformation, some permanent deflection and damage of those elements. Now, when I go to the release subcase, it's going to slowly increment that pin back to 0. So if we look at increment 20 of the second subcase, that will be the pin back at 0. The pin returns to its place. But you'll see that if you look closely, this beam, this red line shows where the beam originally was, and you can see in the middle here, it's deformed such that there's a permanent deformation of the beam in those areas. So there's some residual stress and strain in the model. So it shows me which elements are displaying that permanent deformation, and I can see what that permanent deformation is. So if I look at displacement, I can see that there is about a little less than 1 millimeter of permanent deflection in that plastic beam. So it allows me to see the maximum displacement of the pin and then the permanent deformation of this plastic bar when I release that load back to 0. So really, really great representation of really all the factors of nonlinear statics here. Looking at large displacements, looking at permanent material deformation, and really combining those together nicely here. All right, so the second example I wanted to show was the most complex type of nonlinear static, and that's going to be your boundary condition nonlinearity. So in this case, I have a buckle here. So I have this little snap piece, and then the fitting down here for the snap fit. So it's going to be pushing really the same thing as the last example. It's going to be moving this back face forward. I don't remember the exact value. I think it's like 1/2 inch. So it's going to be moving this forward 1/2 inch, which will push this buckle here down through the snap such that this is going to deflect backwards, and we'll be seeing a significant amount of stress on the snap fitting. We'll also be seeing a lot of new contacts being created as this slides through the buckle. So this is something that requires nonlinear static, or maybe even a potentially nonlinear transient analysis. So with this specific example, you'll notice I did something that I mentioned in the PowerPoint, and that is limiting unnecessary translation and rotation. If you don't limit some of the excess rotations and translations, you can get an analysis that will take hours to run, and really you're going to be getting the same result. So I applied a fixed constraint to our fitting. So this orange part here is basically fixed such that it can't move. And that's obvious because I'm focusing my analysis on the snap. I don't really care much about this buckle piece breaking. It's over-designed already. This is the part that I'm concerned about breaking. I applied an XZ constraint. So I've applied a constraint to all of these blue faces shown here. So if I rotate this around, you guys can kind of see what I did. So all of these faces in blue on this snap are constrained. And if you look at the degrees of freedom I have available, I've allowed for the X direction and the Z direction translation to be available. Everything else is constrained. So looking at my coordinate system, the X direction is going to be this way, which will allow for this to bend inwards and outwards. So the part can bend back and forth, which is going to be the most damaging motion. And then Z, so the whole thing can move in the positive or negative Z direction. So this can deflect backwards and the whole thing can move forwards. So I could probably allow for an additional degree of freedom, maybe some rotation about the Y-axis. Maybe I want this thing to be able to rotate. I might run it like that to see what kind of rotation occurs. But in this case, what I'm basically saying is that I'm treating it as though it can only move along the Z and X direction, which will help the solver to limit the unnecessary degrees of freedom. And I'll converge on a result much quicker. And I'll still be able to capture the maximum amount of stress that I will see as this bends kind of right in this curved area of the snap. So I'll still be capturing the data that I need, but it makes it easier on the solver because this can't start to wobble, so it can't like rotate down this way or translate vertically in the Y direction, so it can't come up off that surface, which would also create a lot more rotation. So I'm simplifying the degrees of freedom to make it easier for the solver. So looking at the result we get, basically I did a total of 60 increments. Like I said, when you have nonlinear contact, usually 50 to 75 increments will work. So I did about 60 increments. And if you look at this like halfway, so let's say 50%, so increment number 30. I'm going to go ahead and display this. It'll show it being pushed through the buckle. And you can see here, it's deflected quite a bit. And you can see the contact created on this side edge here, as well as the contact and the bending in the middle here. So it's going to be constantly recreating these contacts. So here we have contact in this far side of the buckle at the beginning of the analysis. So let's go back to like increment 15. The contact is occurring at a different part in that buckle. So that's why we need nonlinear statics, is because the contact point is changing constantly through this analysis as this is pushed through the buckle. So you can also animate this. And when you want to animate a nonlinear static analysis, what you'll want to do is take your results and do what's called a multi-set animation. So if you right-click on results and go to multi-set animation settings, what this does is allows me to choose a start and an end set. So I can go from increment 1 to 60 and observe the entire motion of this and see the stresses and displacements throughout the entire nonlinear static analysis. So I created a video earlier so we don't have to wait for this to buffer. We'll go ahead and pull this up, click play. And you can see the snap moving through the buckle and that contact point changing along the close side here of the buckle. You can see that contact being regenerated throughout the entire analysis, and then it snaps into place. Right at the end, it didn't quite capture the, the snap point, but right at the end there, it snaps into place, showing that the snap made it all the way through the buckle and reoriented throughout the process. We'll play it one more time for you guys. So that multi-set animate is really great because you get, it's froze up on me. you get to observe that full range, and you can really get an idea for where the stresses will peak. That way you don't have to dig through all of your increments to find it. And then you can go back and you can look at each increment individually and really determine if your stresses are within a reasonable working range for the material, or if you need to adjust your geometry at all and rerun it. So just keep in mind with the nonlinear static, you've got really 3 conditions. You've got your material nonlinearity, like this beam, where we're looking at permanent deformation. You've got your boundary condition nonlinearity, like this buckle, where you have new contacts, load paths changing, sliding, hinging. And then your last nonlinearity condition, which is your geometric nonlinearity, and that would be large displacements and deflections, like we saw with this pin, where the pin displaces 35 millimeters and this beam deflects a significant amount. That's where nonlinearity is also really critical. So when you're in your linear statics, to switch over, just remember, if you change your analysis type up top from linear static to nonlinear static, that will give you the ability to modify your material, modify your setup, which is going to be where you specify a number of increments to use. And then from there, it's just fine-tuning your contacts and your constraints, running it, and then seeing what you get. So if you have any questions, follow-up questions on nonlinear statics, some of the settings I went through today, or maybe you have a problem that you'd like some advice on, feel free to reach out to us. We're happy to help, give you some feedback and some advice. And we also have regular training courses if you're interested in any of those as well.